This is chapter 10 on matrix multiplication. So far we've seen, well, a couple of different kinds of multiplication. If you like, you can think of the inner product as a multiplication of two vectors. We've seen matrix vector multiplication. And now we're going to step it up one and look at matrix multiplication. You can multiply two matrices. We're going to see that has a lot of uses. Okay, so if I have an M by P matrix and a P by N matrix, the first one is A and the second one is B. And note that the matrix A has a number of columns, that's P, which is equal to the number of rows of B. That is critical, okay? I can multiply A and B to get another matrix, which I'll call C, and we're simply going to write it as AB. So we're heavily overloading multiplication notation. The ordinary multiplication notation is by simply you put two things together, right? So next to each other. So if I say something like, anyway, you just put them together. And we do that with matrix vector multiplication. But here it's matrix. Okay, and here, to say what C is, I have to tell you what its entries are. And so its ij entry is a sum of products of entries of A and entries of B. And here's what they are. I sum over aik, that's walking across the ith row of A, and I multiply those by bkj. Now here, j is fixed, and so k is changing in my sum, and I'm walking down the jth column of B. And I can write it out that way if you don't like the sum notation. Okay, and so very roughly speaking, here's how you get the ij entry of the product matrix. You move along the ith row of A, and you move down the jth column of B. And you, roughly speaking, take the inner product, or basically you take the sum of the products of the corresponding numbers, okay? So let's do an example. And by the way, you may have seen this in a previous course as well. So I just want to make sure everyone's on the same page. Okay, so for example, here is a 2 by 3 matrix, and here is a 3 by 2 matrix. And the thing we have to check is that the intermediary dimension is the same. So the number of columns of the first matrix is equal to the number of rows of the second. And indeed it is. 3 is equal to 3. And the result is actually 2 by 2. Okay? So before you ever multiply two matrices, you must perform this syntax check just to make sure if it's a valid product. Okay, so this is valid. Wouldn't be an example on the slides if it weren't, but okay. All right, so then let's actually figure out how to do this. Well, the first entry, that's going to be C11, and that's obtained by going across the first column here and down across the first row here and down the first column here. And indeed, it's minus 1.5 plus 3 times 0, which is 0, plus 2. And you should get this, okay? So that should be your number. That's right. So, okay. All right, let's audit another entry. How about, let's try this one, okay? So to get the 2 entry of C, we would go along the second row of A and down the second column. And let's just check it. You get 1 times minus 1. Okay, that's minus 1. Plus minus 1 times minus 2 is 2. So we're up to 1. And then 0 times 0. So we're 1. And it's correct. Okay, so by the way, at this point, matrix multiplication, this is like the rules of chess. It should have no interest. There's no reason you should have any interest in this yet. So you have to take me on my word that this is actually going to be super useful and super important. But for the moment, these are just the rules. This is how you do it. Okay? So there are, we've already seen various types of multiplication, and they're all actually special cases of matrix multiplication. So here's one. We saw the scalar vector product. And we would write it as alpha x, where alpha is a scalar and x is a vector. Now, it turns out that's not a special case of matrix multiplication. It's got the sizes are wrong. Alpha is like 1 by 1, and let's say x is n by 1, right? So you can see the intermediary dimensions don't line up. So in fact, however, if you do scalar multiplication with a scalar on the right, it actually works. It's exactly the same. Now, for some, I guess this is just the quirks of mathematical notation. People don't write a vector with a scalar on the right, although I think what this shows you is they should. But nevertheless, they do. I mean, if someone does that, no one would think, I mean, they would think it's weird, but they would fully understand what you're saying. You could even explain this, and then they go, "Oh, cool! That's even good for you." Okay, so just mathematical notation convention is we don't write a scalar vector multiplication usually with a scalar on the right. Almost always it's in the front, and that's a tradition that goes back probably a couple hundred years by now. So that's how we do it. All right, inner product is actually now. It's a perfect example of this, right? So this says you have two n vectors, A and B, and it says you form the transpose, and so A is n by 1, A transpose is 1 by n, B is n by 1. Sure enough, the intermediary dimensions are the same, and so you can multiply them, and the result's going to be a 1 by 1 matrix, which we interpret as a scalar, okay, or a number, and it is exactly the inner product. Matrix vector multiplication, that's one. So here, A is m by n, let's say, and x is n by 1. And sure enough, you can multiply them. You can think of x as a matrix, and then perform matrix multiplication, and it's the same as matrix vector multiplication. Okay. We can now tell you about something called the outer product of two vectors. So two vectors, by the way, of any size. It doesn't, because it always works. So if I have an m vector A and an n vector B, I can form AB transpose. Now, to figure out what this means, A is an m vector, so it is m by 1, and B is n by 1. B transpose is 1 by n. And sure enough, the intermediary dimension is 1. And when you work out what it is, it creates a matrix, which is m by n. And the entries are all products of all possible entries of A with B. Okay, so that's called the outer product. You've seen the inner product, and you can see they're very close in terms of this notation, right? One is A transpose B, that gives you a scalar, and AB transpose, that gives you a matrix. It's called the outer product. We'll encounter that a couple of times probably. Okay, now matrix multiplication is a bunch of properties that hold. I'm actually not going to show them. I mean, somebody has to or should. You could trust me. That's an option, I suppose, at this point. Or you could audit one or two of these yourself. But I'll go over them and say kind of what they mean. It's super important that you stay on your toes with this notation to make sure everything here works. So here I have three matrices. And the assumption generally is this, is that when I write down products of matrices like A, B, the assumption is that that's a valid product, right? And, so some people would say that they are compatible or something like that. Or it just means the intermediary dimension is correct, right? So what I'm writing down here, whenever you see things like that, the assumption is that everything is correct, right? If I then later tell you A has this dimension, B has this, and C has, then you raise a big alarm and you go, hey, you can't multiply A and B, it makes no sense, or something like that. So, okay. So this says multiply the two matrices A and B first, and then multiply by C on the right. Then it turns out that's the same as if I multiplied the matrices B and C and then multiplied by A on the left. And so what that means is we can write both as the triple product ABC, right? Because what it says is that when you write down the product of three matrices, it doesn't matter whether you multiply A and B first and then C, or B and C first and then A. So that's an important thing. Okay, it distributes. So A matrix times B plus C is equal to AB plus AC. Now you have to be super duper on your toes here. In this equation, first of all, it must be that B and C have the same size. Otherwise, you have no right to add them. No, you don't have the right. It just means nothing if they are not the same size. So presumably in this line, B and C have the same size. And this is the plus, that's the addition of matrices. Okay, so it says add the matrices B and C multiplied by A on the left. Over here, it's different. This says multiply first A by B, then A by C, and then add them. So this is also matrix addition, but it's possibly a different size matrix, right? So, okay. Here's one. AB quantity transpose is B transpose A transpose. So roughly speaking, the product transpose is the product in reverse order of the matrices themselves transposed. I mean, honestly, it's easier just to look at the equation. Okay, so it looks like this, right? Very important rule. And you might not think that, right? Because, for example, aesthetically, you might say, I don't know, this looks reasonable, right? And it looks reasonable. It is very and deeply wrong for many reasons. I mean, first of all, it's just false. But the other thing is, it's a lot of times it doesn't make any sense, right? That depending on the dimensions of A and B, A transpose and B transpose always make sense, but you can't multiply them necessarily. So this is just wrong. Okay. Here's one. A times the identity is A. If I multiply on the right by an identity matrix, I get A. If I multiply on the left by an identity matrix, I get A. And by the way, these two i's are of different sizes. If A is m by n, this I is n by n, that identity matrix. And this I is m by m. Okay, so here you just get things from, you get the dimensions, which are ambiguous because I didn't say what size I is in the two equations. You get it from the syntax of the equations. Okay, now here's something super duper important. It's very important. The product AB is not necessarily equal to the product BA. Actually, it's worse than that. Even if you can multiply AB, there's no reason to believe that you can multiply BA. It may be incompatible, okay? But even when it does make sense, even when AB and BA are both valid products, they need not be equal to each other. Now, of course, in some cases they are. I'll give you an example. A times I equals I times A, and A has, let's make A, yeah, we'll just leave it this way. A is square in this case, right? So the two i's are the same matrix at the same size. That's true. By the way, when two matrices, when you multiply them together and you get the same result, they have to be square. If you get the same result, no matter which order you multiply them in, that's called commutative. They commute. It means you can kind of put them in, you can multiply them in either order, okay? But in general, that doesn't hold. That's a very important fact. Okay, now block matrices will work with matrix multiplication. So for example, here, first of all, this would simply be the formula for if A, B, C, D, E, F, G, H were numbers. This would be a 2 by 2 matrix, 2 by 2 matrix, and that's a 2 by 2 matrix. And this is indeed the correct formula for what happens when you multiply two 2 by 2 matrices. However, what's cool here is that these could be blocks. So that's a block 2 by 2 matrix. These are block matrices. So A, B, C, and D can themselves be matrices, as can E, F, G, and H. Now, for all of this to make sense, everything has to, any matrix I write down here when I'm multiplying has to have the right, things have to have the right dimensions. Otherwise, this is all, well, it's meaningless, right? But if these are valid products, then this identity holds. So it says that we can do matrix multiplication by blocks, which is actually kind of cool. One very important thing, and that goes back to this fact, is when you're messing with matrices and writing down equations, you have to be very careful with the order of them. So AB is not BA. So don't do anything that depends on AB being BA, which you're used to because that's true for numbers. The product of 2 and 3 is the product of 3 and 2, but the product of two matrices in reverse order, when it makes sense, need not be the same as the other one. So just be super careful about keeping the order right. So for example, in this formula up here, if A, B, C, D, E, F, G, H were numbers, I could remove that and write EA. It would be true. It would still be correct because EA and AE are the same provided that they're scalars, right? If, however, they're matrices, they're not the same, and then this, what I've written down here, is just wrong, okay? So you just have to be very careful. It's order matters. Okay, now we'll give a couple of interpretations, and we'll be using all of these basically throughout the sequel, the rest of the course. So if you denote, let's first write out B in the product AB as columns. Okay, so it's B1, B2 up to Bn, right? So, and remember that B is going to be P by N, and A is going to be M by P. This is A, and this is B. Okay, so it's going to look like that. And if I work out what AB is, actually I can do this by block matrix multiplication. So I simply write B as a block matrix where the blocks are the columns. And then I just multiply out as if these were numbers or whatever, and I get, being very careful with the order. And I get AB1 and then AB2, and each of these is a column. And so now what you can see is one interpretation of a matrix A times a matrix B is it is simply, it works column by column. It just says take the matrix B, multiply every column of B by A, and then rearrange them into a matrix. So you could think of it as, some people think of AB as a batch multiply of A times all the columns of B. So that's one way people think of it. As an example, we can represent multiple sets of linear equations with a very compact notation. So remember that a system of linear equations looks like AX equals B. That's a system of linear equations. If this is if A is M by N, this is M equations in the N variables, which is X. B has size M here, has dimension N. M. Okay, but now suppose we have multiple linear equations, but with the same coefficient matrix A, but with different right-hand sides, BI. Well, we can write that in super compact notation this way. And now I have basically a system of linear equations. X is a matrix, and it literally means that its columns are the different X's and B's are the different B's. So that's, by the way, this is going to be important later in the course, but this is kind of the idea. So it's super compact notation if you write stuff out this way. Okay, another very useful interpretation for us is going to be the inner product interpretation. So as you know, to calculate an entry of the product, you go along the row of A. If it's A times B, you go along a certain row of A and down a certain column of B. Very roughly speaking, you're taking the inner product of a row of A and a column of B. Well, we can write it out this way. We can say that AB is the following matrix. It's the first row of A times, I should say, the first column of B. That's A1 transpose times B1, and so on. And so what it is you could think of this as a matrix product gives you all the inner products of the rows of A and the columns of B, and then arranged into a matrix. So that's a perfectly good way to think about matrix multiplication. It's useful. Actually, all these different ways, they're not very hard to work out. They're all related, and they're all useful in different settings. So here's a matrix that's going to come up pretty often in the sequel. It's called the Gram matrix. That's the name of Gram is the name of a mathematician from the 19th century. So let's let A be an M by N matrix, and its columns are A1 through AN. And each of those is an M vector. Okay, well, the Gram matrix is simply this, it's a very compact notation. It's G equals A transpose A. A transpose A, that's something you're going to be seeing a lot of, to be honest, so get used to it. But it's got a beautiful interpretation. So the entries of A transpose A are exactly the following. They are, the first entry is A1 transpose A1, but you know what that is. That's actually the norm squared of A1. Okay, so the 1, 2 entry is the inner product of the first and second column. Okay. By the way, the 2, 1 entry is the inner product of the inner product of the second column of the first. But you know that inner product does commute. So these are the same number. And what that says is the matrix G is a symmetric matrix, right? Which means that if you transpose it, you get back the same matrix. It means that its ij entry and its ji entry are the same. Okay, so anyway, this is the Gram matrix. It's super useful. We can also use super fancy. We can use matrix arguments to show that G is symmetric. So if I say that if I want to know what is G transpose, well, that's A transpose A transpose. Okay, but that's the product of two matrices and then transposed. But we know what that is. That's simply the transpose of the second matrix and then times the transpose of the first matrix. So this is equal to A transpose times A transpose transpose. But wait a minute, A transpose transpose is A. If I transpose a matrix twice, I get back the matrix. So this is actually A transpose A. Hey, but that's G. And this string of equality says that G transpose is G. That means G is symmetric. Okay. So here's something you can do with the Gram matrix that it gives you a very compact way to describe a concept that we already have. It's A transpose A equals I. Super interesting. It means that if you look at this matrix here, it's ones on the diagonal and 0 off. Let's see what that means. Well, if A1 transpose A1 is 1, that means the length of the norm of A1 is 1. Same for A2. And so what it says is the diagonal of the Gram matrix is equal to, they're all ones, provided all of the columns of A have the same norm, which is 1. Okay, so that's normalized. But now let's look at off-diagonal entry. If this is I, it means the off-diagonal entries are 0. So that says that A1 transpose A2 is 0. That means that A1 and A2 are orthogonal. But so are A1 and A3 and A1 and A4 and so on. And so basically, the super compact equation A transpose A equals I is a way to say that the columns of A are orthonormal. They each have norm 1, and different columns are orthogonal. They have an inner product of 0. Okay, so this is the Gram matrix. Let me say a little bit about the complexity of multiplying two matrices. Actually, this is a super interesting topic. I might say a little bit about it in a minute. But so the basic way is here is A is M by P, and then B is P by N. Okay, so now to get an entry, and every entry of C is basically an inner product. And what I'm going to do is, you know that the number of flops to calculate a P-long inner product is actually 2P minus 1, but we skip the minus 1 and no one pays any attention. It's just 2P. And so C, you have to get all the entries of C. C is going to end up being M by N. So I have to do, for all the entries, I have to calculate an inner product, and I get 2 MNP flops. So basically, the total number of flops required to multiply two matrices is the product of their dimensions. Well, the intermediary dimensions, which have to match on the two matrices, have to be the same. And so it's the product of the three numbers. That's it. So, for example, if I were to multiply 2,000 by 1,000 matrices, that requires 2 billion flops, right? So, by the way, this is a lot, right? I mean, these are big. I mean, if you think about it, these are very big. Like if someone says, what's 1,000 by 1,000 matrix? You'd say, oh, it's a rectangular array of 1 million numbers. It's a lot, at least to a person. It's a whole lot, right? And then you multiply the two together and you say that would require 2 billion floating point operations. So if you had to do this by hand or with a slide rule or an abacus, it's going to take you a long time. On my laptop, which is way old now, I can do this in about 0.1 seconds. Okay, so that's crazy what I just said. And actually, it's a very important, all the math we're doing was just as true and just as interesting in 1830 or 1880 or something like that, or 1950. This is what you didn't have in 1950, was the ability to actually do the calculations that we're talking about in this course at truly stunning speeds. So this is just stunning. So I guarantee on your homework, one of your homework problems will be to multiply 2,000 by 1,000 matrices, and then have a moment of quiet to sit there and appreciate how like awesome that is. That the little processor in your laptop or whatever you're doing this on, for that matter, you could do this on a phone. Okay. But the point is to sit there and have a moment of silence to just recognize how awesome it is that 2 billion floating point operations were just carried out for you in about a tenth of a second.